talked only about simple linear regression where we have one predictor x and the predictant y. When we have multiple predictors x1, x2, x3 and so on, then we call this modeling exercise a multiple linear regression analysis. Now, in the sales versus advertisement example, for example, X can be the expenditure on advertisement, X1 can be the expenditure on advertisement, X2 can be the average uh, income of the targeted population where you are selling PepsiCo, X3 can be what's the city, which city you are staying in, and maybe it's whether it's a metro city or not. X4 can be the average age of the population you are targeting to sell Pepsi and so on. So you can have multiple predictors. However, please note that in all these problems, predicand is only a single random variable. Again, here I would like to remind you that x1, x2, etc. Though those variables can themselves be random, in the whole analysis they are not treated as a random variable. So the only random variable here is y. All right. So this is a multiple linear regression formulation where x1 to x1, x2, x3, etc. to xd, these are all the predictors. If I write in vector notation, then x belongs to d-dimensional real values. Although you may have one of the predictors may not actually be real also, like I gave you the example of whether the city is a metro city or not. So in such a case, it is possible to use dummy variables as indicators of the categorical predictors. So an example can be, instead of using x3, which is a categorical predictor, we use another variable z, which takes a value of 1 if metro city or 0 otherwise. Okay, and so on. So you can use different types of dummy variables and so on and so forth. So we can have the predictors, they can be either real valued or they can be categorical as well. Remember here that y, the predicand, has to be real valued and it has to belong to the normal distribution. That is the basic assumption here, right? So again, to recall, the distribution of y changes with different levels of x. Now here x is a d-dimensional vector. Okay. For multiple linear regression, we are not going to discuss in much details. I give this as a reading assignment to you. So if you refer back to our textbook, James et al. Introduction to Statistical Learning, there in the simple linear regression chapter, they have a section called multiple linear regression. So that section is a reading assignment for you. And when you read about the hypothesis testing there, remember we were trying to do hypothesis testing for the simple linear regression case. If we are trying to do hypothesis testing for beta 1, then the null hypothesis was beta 1 equal to 0 against the alternate that beta 1 is not equals to 0. Now in case of multiple linear regression, the alternate hypothesis is changes very subtly, and here if we are to check the significance of the individual predictors, then our null hypothesis will of course be any of the betas is 0. So beta j is 0, that's our null hypothesis, and for all the j's, so beta 1, beta 2, beta 3, etc., they are all zeros. That's the null hypothesis. The alternate hypothesis is that at least one of them should be non-zero. So at least one beta j is non-zero. J varies from I to 1 to d, where we have d many predictors. So if let's say you have two predictors, x1 and x2, then you can plot the variation, the scatter between x1, x2 and y in a three-dimensional plot. The moment it becomes more than 3 dimensions, we cannot visualize. So that's about hypothesis testing for multiple linear regression. Now kindly note here that there is an inherent assumption that these predictors x1, x2, etc. must not be correlated to each other. So if you are trying to fit a model and the predictors are correlated to each other, you cannot fit multiple linear regression models. You can in fact use some techniques to transform these predictors into a space where they are no longer correlated, and you can also do some dimension reduction techniques on them. So you remember in the first module we had discussed that dimension reduction is an aspect of unsupervised learning. So in this course we are going to learn some of such techniques where you can actually transform correlated data to an uncorrelated data set. However, the moment you are applying multiple linear regression, you are assuming that the predictors are not correlated to each other. Now, the way I have written the model here, you can model the individual effects of each predictor. Not just the individual effect, we can model the joint effect also. And there's a very simple way to do it. So instead of looking at only the single terms, we can consider another predictor which is simply the product of those two predictors. So if let's say you have one predictor x1 and another predictor x2, then you can include another term in your model which represents the so-called interaction term. And the idea here is that you may have, let's refer back to the sales versus advertisement again. So x1 may be advertisement and x2 may be the age of the target population. Then not only will they have individual influences on the sale, but they can have their joint presence together. They can have another effect on y, and that you can consider. It is possible to consider the joint effect by considering the interaction term in multiple linear regression. Now that we have discussed in details about simple linear regression and multiple linear regression, let us quickly recapitulate some of the important assumptions and issues that we need to consider if we are applying SLR or MLR on any dataset which is of relevance to us. You might be working in an industry or you might be doing your research. If you're applying, then if you're applying SLR or MLR, then these are some of the assumptions and issues that you need to be considerate of. So about the errors, of course, we have made three important assumptions. The first one is that errors are uncorrelated, then they are normally distributed, and they are homoscedastic. So essentially the error terms are white noise, so mean zero, variance sigma square, and they are IID normal, independent and identically distributed with the normal distribution. So independent takes care of the uncorrelated term, then they are normally distributed, and their variance is also constant, so the homoscedastic assumption. Now there are ways and means to check these assumptions and how they are holding true or not. There's a plot which is a diagnostic plot called the residual plot, and I'm going to discuss about residual plot subsequently in greater details. So this is a diagnostic plot which can help us test whether these assumptions are true or not, and whether they are normally distributed. This can be very simply and visually tested. We have all the residuals, right? We have all the epsilon i's, and we can simply plot a histogram. If it represents roughly the bell shape, then we can assume that they are normally distributed. However, if the histogram shows heavily skewed behavior. We know that the normal distribution is symmetric. If the histogram is heavily skewed, then perhaps the errors are normally distributed. That assumption is not correct. Okay, then you cannot apply simple linear regression or multiple linear regression. Then there is another important assumption, and that is that the relationship between x and y, the predictor predictand relationship, is linear and additive. Again, if the relationship is non-linear, then this is not the model to fit. If the responses of the predictors cannot be additive, I mean they might be they might be influencing y in different functional forms, and all of that, this simple linear regression or multiple linear regression model will not take into consideration. If we have outliers in our data set, we may need to discard them. So that's also an assumption. Remember, we have been harping on this point again and again. Simple linear regression and multiple linear regression models are models about the mean. So they perform, you are more confident about anything that you conclude from this model in the range of the means, right? And lastly, collinearity of the predictors. If you have multiple predictors, then they must not be correlated with each other. Let us now talk about the residual plot. A residual plot, as the name suggests, is just a plot of all the residuals. So on the y-axis, we plot the residuals, epsilon i's. Again, recall, epsilon I is nothing but yi minus yi hat, observed value minus the predicted value, right? Now on the x-axis, so on the y-axis we plot the epsilon i's. On the y-axis we can plot either x or y. However, when we have multiple x's, x1, x2, etc., for multiple linear regression, when we have many predictors, which predictor should we choose as the x-axis? So therefore, in the x-axis we choose the fitted y's. So fitted values is what we have in the x-axis, and on the y-axis of course we have the residuals. Now if we have a residual plot which does not show any pattern, then our assumption about the epsilon i's, that they are uncorrelated and independent and identically normally distributed, and they are homoscedastic, all of that will hold true if we do not see any major patterns in them. If we do see a pattern, then it means that your model perhaps is not a good model, and that's why this plot is called a diagnostic plot. You know, when we fall ill, we go to a diagnostic center which will check our blood or our sputum or anything like that. So it carries out tests to see how good we are doing. So similarly, the residual plot is called a diagnostic plot because we are testing how good the model is doing. And if you compare these two plots, A and B, then we see that A shows some kind of a pattern. So the values come down and then they go up, and also the density of points is lesser here as compared to here. So therefore, in case A, it's perhaps this linear regression model is not a good model. Whereas in case B, we see roughly, I mean, the fitted straight line to the residuals more or less is horizontal. You will never have a perfectly horizontal line. It's more or less horizontal, and we see a scatter which does not show much of a pattern. So therefore, in case B, perhaps a simple linear regression or a multiple linear regression, which whatever the case may be, that's a good model. You may also end up having residual plots which look like this: C versus D. So these two plots, C and D, are from the same data set, and A and B are also from the same data set. I mean two sets of data sets, but some kind of tweaking has been done, and you can either transform the data to some other variable. So let's say in one case we fitted a model between y and x, and in the other case we fitted a model between log of y and x. So same data set, that's why you see equal number of points in the scatters C and D. But out of C and D, which one would you say is, for which one is the linear regression a good model? In our assessment, D is the answer, because in C you see that the residuals show some kind of a conical shape. So the spread of data, the residuals here, is much less as compared to here. However, remember we have made the homoscedastic assumption, that is the spread in these residual terms, the standard deviation of the epsilon I, sigma, is constant. However, we see that as we proceed along the x-axis, that spread increases. So therefore, in case C, perhaps the homoscedastic assumption is not being satisfied. Again, in D, we don't see that kind of a problem. It is not a perfect horizontal line again. In real data sets, you would seldom end up with a straight line which is perfectly horizontal. So in between C and D, D is perhaps a good model if you're applying simple linear or multiple linear regression. Now, the residual plot may also be used to detect outliers. Detection of outliers. So here in this figure we see that when we plot the fitted values versus the residuals, all the points lie close to each other in this zone, except one point which is indexed by the number 20, this point which is marked in red and other points are marked in black. You see that this point lies far away from the other points, and this is perhaps an outlier. An outlier can result either in because of a measurement error or because of some kind of a discrepancy or singularity in the data set. So we would typically want to exclude that outlier for the subsequent analysis for fitting the simple linear or multiple linear regression model. So with this, we come more or less to the conclusion of module 3, which is our discussion on linear regression. Now, you see there are many approaches to study simple linear regression, right? As the name suggests, it's supposed to be simple, but it forms the foundation stones of any statistical learning model, and therefore one can study it to very many great depths, right? We have tried to reach to a depth which in my opinion is practical, but there are lot many things which we have not in fact discussed about this topic in this course, and we will not be discussing them further also. For example, the first thing is some proofs or theorems that we have not talked about. We have not seen how we can prove the fact that if you have a random variable, x1, x2, etc., sets of random variables, then their transform variable, how it belongs to the t distribution, or how the distribution, the sampling distribution of sigma hat, which is given by RSS by n minus 2, why that should belong to the chi-square distribution. So those are some proofs that we have not talked about. It's possible they can be proved, but the proofs are quite involving and clearly outside of the scope of this course. So these proofs, if you are really further interested, statistics is a very deep subject, and if you want to take it up further, please feel free to read about these proofs, and please also share with the rest of the class if you find something interesting. The second thing that we have not talked about when it comes to linear regression models is the F-test. So we have talked about hypothesis testing on the parameters beta naught and beta 1, and we have talked about how to get the confidence intervals. We have also talked about getting the confidence interval of the mean response and the prediction interval of any future y. However, we have not talked about F-test, which is used for comparing two models. That we have not talked about. The third thing that we have not talked about is the analysis of variance ANOVA ANOVA analysis, and ANOVA also has several extensions such as ANCOVA, analysis of covariance, and so on and so forth. All of that we have actually avoided in this course for brevity. Those are related topics. Unfortunately, it falls outside of the scope, the current scope of this course. And finally, though we have done hypothesis testing on beta naught and beta 1, we have not done hypothesis testing on the correlation coefficient, on Rxy, the correlation coefficient. Now, what do I mean by that? So let's say you have two variables. Maybe one can be stream flow in Mithi river in Mumbai, and the other can be Oshiwara river, which is also in Mumbai, right? And we want to test whether the correlation between stream flow in Mithi and stream flow in Oshiwara, they are correlated or not. Now, of course, you can, if you calculate the correlation coefficient and if you get a value close to 1, you can reasonably be certain that perhaps they are significantly correlated. However, in reality, you will seldom find data sets which speak so clearly. So you may end up somewhere getting a value in the middle, maybe 0.4 or 0.5. Given the size of your data, given their sampling variability, is that correlation coefficient significant or not? That's what is tested in hypothesis testing on the correlation coefficient, which also we have not talked about in this course. So with this, we come to the end of linear regression.